Thank you everyone for coming to my presentation. Today I will be talking on multi-conductor transmission line theory and its applications to modern metamaterials. Again, I am a PhD candidate in the Department of Electrical and Computer Engineering at the University of Alberta in Canada. So I work out of the Microwave and Metadevices laboratory under the supervision of Professor Ashwin K. Iyer. And our laboratory has several state-of-the-art equipments that we used in some of the work I'll be talking about today. On the fabrication side, we have a couple of LPKF milling machines. On the measurement side, we have a 40 gigahertz Keysight Technologies PNA for measuring our circuit-based devices, and as well for doing our antenna measurements. We have an NSI near-field scanner inside of a shielded anechoic chamber. To inspect all the devices that we make, which are occasionally filled with submicron features, we have a 100 times zoom microscope with 1080p digital resolution. So a lot of tools for rework of our devices, and we're able to do a lot of our prototyping right in-house. I'm very privileged to be able to work out of this lab. So today I'll be going over a quick background on transmission line theory, its history, and some fundamental properties of the transmission line modes. And then I'll be hopping right into the bulk of this presentation, which is multi-conductor transmission line theory, and looking at a lot of specifics that aren't often talked about, such as how we define multi-conductor transmission lines, and what are the domains of representation that we use to discuss multi-conductor transmission line phenomena. Then I'll be looking at the mathematical formalism of how we do domain transformations, which are essentially just a change of bases. Then I'll be going from here into the theory of multi-conductor transmission line based metamaterials, a quick history of development there. Look at the Bloch modes that these structures support, and how these Bloch modes couple to form the interesting dispersion phenomena that we're looking for out of modern metamaterials. Lastly, I'll be going over some applications of this, what we've done with our work, what others have done, and looking at future directions of what we want to do with these metamaterials, which is the focus of my PhD research. So to start with, transmission line theory was really in core developed by Oliver Heaviside. There were many contributions from others, but he really worked to formalize a lot of the ideas and concepts that we use today. So he actually got into this by working as a telegraph operator out of Denmark. And he actually operated on a cable that was newly laid between Newcastle in the UK and Denmark. And while operating on this cable, he noted several technical limitations that he was curious about. Why does it require very high voltage and current in order to operate this cable with regards to what you would expect from an overland cable? Why is there more signal distortion than one would want? Right? How can these problems be mitigated? And so he had come across a copy of Maxwell's newly published work on the propagation of electromagnetic waves. So he worked on deriving similar equations describing the propagation of voltages and currents in this type of environment, in this cable. So a two-conductor, one-dimensional environment. And of course, these are known today as the telegrapher's equations. And interestingly enough, if you look at his actual work, what you see is that the equations he used are essentially the same as the ones we use today, just a small change in notation. So transmission line theory really at its core deals with the investigation and modeling of transverse electromagnetic modes that are supported by two parallel conductors. So sorry, there's just one mode supported here, this transverse electromagnetic mode. And what transmission line theory does for us is that it allows us to express the vector electric and magnetic fields around these conductors as scalar voltages and currents. Right? Now, this may seem very elementary, but it's actually a very critical concept because what it allows us to do is express waves in these transmission lines by combining the telegrapher's equations, of course. And we know that we can derive wave equations in terms of both the voltages and the currents, in terms of the propagation constant shown in the bottom left and characteristic impedance shown in the bottom right. These are very canonical concepts. But the applications of transmission line theory specifically are very broad, right? It's used in multiple different areas, but critically, we want to use it in devices whose physical sizes are on the same order of magnitude as the wavelengths they respond to. So in these types of scenarios, phase is a very critical concept. And in order to apply transmission line theory, we have to be able to control it in our device to a very high degree of precision. And of course, we can do these with these microwave circuits that have been developed over the last half century or so. And of course, we know how to employ those, right, to create couplers, filters, etc. But transmission line theory in particular allows the integration of electrical propagation effects into classical circuit theory. So while classical circuit theory just deals with lumped components like capacitors, inductors, resistors, etc., the integration of transmission lines into these circuit environments allows us to model other effects like time delay, pulse dispersion, input impedance, etc. So it's a very critical tool to model and analyze modern circuits. Now, multi-conductor transmission line theory is an extension of the transmission line theory concept. So this concerns the study of more than two parallel coupled conductors. And in general, what we assume is that all of these conductors are coupled together, right? So they exhibit mutually induced capacitances and inductances. And this allows us to really change these telegrapher's equations into sets of linear equations, as shown here. Right? This is a pretty well-known phenomenon, but interestingly enough, the history I don't think is really well fleshed out in the literature, because who was one of the first people to work on this? Oliver Heaviside, once again. In his 1880 paper, he actually worked on sort of formalizing the interaction between these various conductors in terms of potentials and charges. Later on, Louis Pipes really worked on summarizing that notation into modern matrix formalism. And Stefan Rice was pretty pivotal in changing the notation that was previously used into the notation and concepts that we use today. So in summary, we know that we want intuitively to express the voltage and current quantities that we see on a per conductor basis. And this just comes from extending the transmission line theory concepts. So the voltages in a multi-conductor transmission line are expressed with respect to a reference conductor, which we typically number as conductor number 0. So as shown here on the left-hand side, the voltages are all with respect to the 0 conductor, and the currents are investigated and really specified on each conductor as well, with the general assumption for transmission line systems being that the currents balance, they all sum to 0, such that it's always implied that the reference conductor contains the negative sum of the currents of the rest of the conductors. Sorry. And we know that physically we can express this, the equations for these multi-conductor transmission lines as a nice compact form using matrix notation. And of course, I've shown these here. We have on the top the equations for induction, relating voltages and currents on the multi-conductor transmission line sections, and the wave equations written in terms of the per unit length admittance, the Z matrix, impedance rather, and the per unit length admittance, the Y matrix. But representing these quantities as using matrix notation raises several questions, right? How do we describe a wave using this notation, right? If we have a matrix and a set of vectors corresponding to voltages and currents, what is a wave, right? How do we define the properties of this wave, right? Propagation constant, characteristic impedance, etc. What if we have an inhomogeneous transmission line cross-section, and there are various materials here which support differing wave velocities in each of those mediums? How do we describe the velocity of this wave? And this is really where multi-conductor transmission line theory sort of shines. Because if we look in depth into how we would represent a single wave, the essence of it is this: a wave has corporate propagation, right? That is to say that the field components of a wave all propagate at the same speed, right? So I've given a figurative depiction here in the figure. And essentially, if we had fields around these conductors, we would see that all of these fields propagated at the same rate along the transmission line in time. Right? So we would actually express this as the wave equation shown here in the middle. So we have a set of voltages and currents which all travel or incur phase at the same rate. And of course, we know that on a transmission line, the behavior we see is actually the superposition of two waves traveling either direction. But the important point here is that all the voltages and all the currents propagate at the same rate. So even though we have a set of voltages and currents, it would be extremely convenient for us if we could express these quantities as the properties of a single wave, right? So instead of a set of voltages, we just had one voltage corresponding to the voltage of the wave, right? How do we do that? Well, we have a formalism which we refer to as modal analysis, and we call these voltages and current distribution modes. So similar to how a two-conductor transmission line supports one TEM mode, multi-conductor transmission lines support multiple such modes. And so we really end up having two main descriptions with which we can describe the voltage and current quantities of a multi-conductor transmission line, and by extension, various other properties. And these domains of representation are known as the terminal and modal domain. So shown on the left is the terminal domain description. So in this domain, we want to describe the voltages and currents of each conductor, right, with respect to an established reference. And to make this clear, we give the voltage and current quantities a subscript T. Now also, various quantities such as the per unit length capacitances of the lines describe coupling between all of the conductors. And so we represent these as fully populated matrices in general. So for example, the per unit length capacitance in the terminal domain is represented by C subscript T, and that's a fully populated matrix. Now, the modal domain, I need to emphasize, is a equally valid method of representation of a transmission line. So in this domain, we are expressing the voltages and currents of each mode. So we use a subscript M to describe these properties. And the various quantities, such as the per unit length capacitances in this domain, are completely decoupled from each other, right? That is to say, the waves are essentially independent. So we represent these properties as diagonal matrices. And this just means that there's no interaction between these modes. So there's actually a formalism for relating the two different domains. And we can derive this analytically. I've gone through it in summary here. So to start with, if we have on the top left the voltage and current waves on each conductor described in the terminal domain, and we combine this with the wave equations that we've derived previously from the vector form of the telegrapher equations. That's on the right-hand side. We end up with the equations on the bottom. And these represent a scalar value multiplied by a vector to a matrix multiplied by the same vector. And of course, you would recognize this as an eigensystem, right? So we know that when we're solving this eigensystem, what we actually do is we compute all of these eigenmodes simultaneously. So we would take that equation those equations on the left-hand side, and we would actually compute the system on the right-hand side, where what we've done is we've expressed all of the eigenmodes simultaneously as the matrix gamma m squared. So this is the diagonal matrix of the squares of the modal domain propagation constants, where each entry is a square of the valid modal propagation constant gamma, as indicated. It's a diagonal matrix, so again, there's no coupling between the modes, as is required for the modal domain values. The matrices TV and TI are the eigenvectors of this system. So these are matrices, each column of which is a valid eigenvector corresponding to the eigenmode, gamma squared m. And these are the eigenvectors of the voltage propagation equation or the current propagation equation, respectively, depending on whether we're talking about TV or TI. And this is actually an important concept because these matrices allow us to change the basis between the modal and the terminal domain. So mathematically, we can do that by simply taking our eigenvector equation and reinserting it into the wave equation to get the set of equations shown on the top right. Where if we look carefully, we note that we have a certain quantity, the inverse of the TV matrix multiplied by the terminal domain representation of the voltages. Representing the propagation in the modal domain. So what we do is we define these quantities as the modal domain, voltages and currents, as shown on the middle left. And if we take these quantities and we just do a basic substitution, what we find in that middle equation here is a set of wave equations in the modal domain. So what we've done here is we've now changed the basis from the modal domain to the terminal domain. So these transformation matrices, as they're called, TV and TI, right? The eigenvector matrices relate the terminal domain to the modal domain. And this is sort of a critical transformation because as you'll see in multi-conductor-based metamaterials, what we do is we take terminal domain systems and we want to understand what are the modal quantities. So we will be using this shortly. I want to note that this change of basis is not a new idea. Once again, Oliver Heaviside indicated that he was investigating this type of change of basis. He says in his work, we may represent the actual potentials of the lines, that is the terminal domain, as linear functions of the potentials of an equal number of imaginary lines, having no mutual influence. And that, of course, is the modal domain. So now, MTL-based metamaterials are evolved from the base class of metamaterials, which of course are artificial composites supporting bulk behaviors not found in naturally occurring materials. And of course, we know that metamaterials support a rich variety of dispersion features with numerous applications. I'm assuming you're familiar with those, so I won't be going into all of them. But basically what I've shown here on the left is a very canonical metamaterial medium, right? Split ring resonators and wires. And we know that this supports a number of interesting wave phenomena. Interestingly enough, metamaterials themselves come from a rich history of artificial media. And some key players in the development of artificial media were Winston Koch, who worked on metallic lenses. So he performed radio wave beamforming using these lenses composed of just thin metallic plates. Walter Rotman investigated artificial plasmas at microwave frequencies by investigating how fields interacted with periodic arrays of thin wires. Gabriel Krohn is noted for his work on equivalent circuit models to represent Maxwell's equations of electromagnetic waves propagating through certain media. And his work actually led to the development of some realized form of these networks, and that sort of forms the basis of transmission line metamaterials. Now, a subclass of artificial media would be artificial transmission lines. And once again, we find that Oliver Heaviside was actually one of the first to investigate this field. So what he had proposed was that we know from our Heaviside condition that these transmission lines can be created to be dispersionless if there's a specific relationship between the transmission line properties, right? Inductance, per unit length inductance, resistance, conductance, and capacitance. And so to meet that condition, he actually proposed homogenizing transmission lines with a higher inductance by inserting periodic loading series inductors. Unfortunately, I wasn't able to find an original reference for that, but I think that's pretty well known in the literature. Michael Pupin sort of extended this work in not only being the first to patent those periodic loading inductors, which are now called Pupin coils, but he also inserted shunt capacitors into a system of series capacitors and shunt inductors, which he modeled these very long telegraphic transmission lines in his laboratory with physically short lines, so that he could understand the exact mechanisms of phase propagation. And this idea is sort of what's used in the development of transmission line metamaterials. So similarly, transmission line metamaterials are periodically loaded transmission lines, but they exhibit phenomena found in conventional metamaterials. So typically these are created by inserting series capacitors and shunt inductors into transmission lines in 1 and 2 dimensions, as shown here. And transmission line metamaterials have numerous advantages, such as they are very simply modeled. They can be very rigorously analyzed with good agreement between the theoretical formalism and what we would see in experiment. And the concepts are scalable from DC to infrared frequencies. And I've shown some examples here. These are both by my supervisor, Ashwin Iyer. He was very pivotal in establishing this field. And in particular, the metamaterial phenomena that we're most interested in is the existence of left-handed or backwards propagation bands. And these are found only in metamaterials. And these bands are such that the phase and group velocities are contradirected. So if we looked at the direction of power flow and we looked at the evolution of phase in time, we would find that these were actually look like they're traveling in opposite directions. And we see these phenomena when we load multi-conductor transmission lines. So similarly, we can periodically load multi-conductor transmission lines with reactive circuit elements to form multi-conductor transmission line metamaterials. So these exhibit behaviors such as left-handed modes, but additionally, we see a host of other interesting dispersion features, such as bandgaps. So I've shown here a circuit diagram corresponding to one of the earliest multi-conductor transmission line metamaterials. This was a work by Francis Alec, And what he examined was the shielded Stephen Piper structure, in which he found that there is a very prominent and controllable band gap. So we note some critical points here. The conductors are loaded with reactive elements, either in series with conductors or in shunt between them, which is a terminal domain representation of this system. But we want the properties of the waves traveling through the metamaterial, right? Because that's what we're interested in from an external perspective. So this would actually be a modal domain representation. So this is where the terminal modal domain transformations come in handy. In fact, they're essential in this process. And I think the understanding of multi-conductor transmission line formalisms is really what enables us to understand all the interesting effects that we're seeing in these complex modern metamaterials. So specifically, what we're looking at in terms of these multi-conductor transmission lines that have been loaded are called Bloch modes. So in addition to being just standard modes supported by these systems, the Bloch modes are representations of these unit cells, these periodic loadings that have been homogenized. So how we compute these Bloch modes is typically we create a unit cell equivalent circuit model, as shown on the top left. We turn that into an ABCD matrix by just cascading the various components. And we use a circuit form of Bloch's theorem, which relates the voltage and current quantities across one unit cell with just a periodic boundary condition. And we get the equation in the bottom right. And of course, you'll note this is another eigensystem, a slightly different form than what we saw in the basic MTL theory, but a similar concept nonetheless. And interestingly enough, because we've loaded these MTLs with frequency-dependent components, right, capacitors and inductors typically, these Bloch modes are also frequency-dependent, unlike the multi-conductor transmission line modes, which we generally assume are frequency-independent. And this means that if we have a dispersion diagram, these modes can overlap with each other or have all sorts of different band structures or just interesting dispersion effects. So I've shown some examples here on the bottom. If we take the red mode, this is sort of representing a standard right-handed forward mode in which phase and group velocities are co-directed. Whereas the blue mode would be a left-handed or backwards wave mode in which group and phase velocities are contra-directed. On the right-hand side, we see a similar right-hand mode, but this also overlaps with another right-hand mode. So the question is, in these systems, what kind of dispersion effects can we get between these modes? How do they interact with one another? And we understand from coupled mode theory that these modes will interact depending on the similarity of their field profiles. So specifically, in regions in which the modes are phase matched, there will be an exchange of energy between the modes. And that actually was described in detail, as shown in the figure on the top right-hand side by J.R. Pierce, who is one of the first to really perform a rigorous analysis of coupled mode theory. And he investigated both of these cases. Francis Ellick, in particular, investigated them in this sort of coupling in metamaterials. And he found that, again, there is, in these band gap regions, an exchange of energy between these modes. So contra-directed group velocities form these band gaps. And that actually arises from the fact that the energy is contra-directed in the two modes while being phase matched. So if we look at the properties of this of these band gaps, of the modes that exist in the band gap rather, what we see is that it's not that there's no energy propagating at all. It's that if we insert power into one of these modes, it's continuously being coupled backwards into the other mode. which carries the power the opposite direction, such that there's a net zero power flow, and it really looks like the input power is just reflecting back in another mode. So this exchange of energy has a number of applications in modern metamaterials. So that's how band gaps are formed as a result of the coupling of right-handed and left-handed modes, as shown in the bottom left figure. But importantly, we also see that in the coupling of two right-handed modes, as shown in the bottom right-hand figure. So we might not see a band gap formation in this case, but there still is an exchange of energy, and we can utilize this phenomenon to create some interesting metamaterial behaviors. So an important point, and a very interesting one, I think, that distinguishes this modal formalism from something that we would see in traditional optical or semiconductor systems, is that if we look specifically at, let's say, band gaps, the existence or the non-existence of modes at a given frequency does not imply that any mode will propagate or not. Specifically, we understand from this formalism that dissimilar modes may exhibit completely unrelated behaviors. And what I mean by that, I think, is depicted in this diagram below. So on the left-hand side, we have a dispersion plot, right? And this supports a number of different modes and a number of different types of bands. And all the other plots, the four on the right-hand side of that, are scattering plots corresponding to the excitation of different modes. And what we see is that they all exhibit different behaviors. So for example, the first mode exhibits a very small band gap. The second mode exhibits a very large and prominent band gap. The third mode does have a band gap region, but it's at a frequency different from the band gap of the first mode. And this fourth mode here doesn't even really see a band gap anywhere. It just propagates through essentially unimpeded. So I think this is really where the MTL formalism shines, because it allows us to compute how various modes respond to our metamaterial. And thus, I think you can appreciate knowing the properties of these modes becomes a critical aspect, especially if we're trying to get certain types of modes to propagate through our metamaterial and suppress others. So specific applications of this multi-conductor transmission line metamaterial formalism are numerous, but I'll go over a few of the canonical ones here. To start with, we have parallel plate mode suppression. The shielded Sievin-Piper structure, once again, investigated in detail by Dr. Francis Alec, really demonstrated a strong band gap region that came about from the fact that we know that the classical Sievin-Piper mushroom structure supports a left-handed or backwards type mode, whereas the upper shielded region supports a right-handed forward mode. So the coupling of these two causes a band gap. And in this region, the parallel plate mode supported by that shield conductor is suppressed. So we know how to tune this. We know how to create this metamaterial in order to create this band gap structure to suppress these parallel plate modes. This idea was taken further to develop systems that could suppress parallel plate modes without the use of vias. This was the topic of, one of the topics of my master's thesis. And what we investigated was how we could couple various multi-conductor transmission line modes to affect this parallel plate suppression, but utilizing multi-conductor transmission lines with field profiles oriented in such a way that we didn't need to use vias. So what we actually did was we loaded a coplanar waveguide transmission line. And the nice thing about a coplanar waveguide transmission line is that all of the series and shunt components can be implemented on the same layer. So as I've shown here in the middle figure, really we can insert series capacitors into this coplanar waveguide and shunt inductors and realize them in the bottom as interdigitated capacitors and strip or meandered inductors. This means that we can realize our metamaterial on a single metallization layer. So simply by removing some copper off of a layer of metal, we can affect parallel plate mode suppression in a very strong and controllable manner. And this is because the conductor-backed coplanar waveguide structure supports not only a coplanar waveguide-like mode, but also a parallel plate-like mode. And we do some dispersion engineering and we cause a band gap to arise. And so this has numerous applications. The first we looked at was the suppression of parallel plate noise. So what we did was we created a band gap ring out of these metamaterial structures. And we put this in a multi-layer PCB environment, and we injected parallel plate modes into this environment through the use of input and output vias, as shown in the top middle figure there. And we designed our metamaterial structure, shown in the bottom left, to support a large band gap, shown in the dispersion diagram, where we note that we do see a unrelated mode propagating through the middle of that band gap. But as we know, that's fine. That's not an issue for us because that mode is unrelated from the parallel plate mode that we're interested in suppressing. So what we find is that when we simulate this structure, we find that outside of the band gap region, we see the fields indicated on the left-hand side of the figures on the right. And this just shows that fields are going everywhere in this parallel plate mode cavity, right? They're not contained, they're not being suppressed. But inside the band gap region, shown on the field plot on the far right, these fields are strongly contained inside of this metamaterial ring, right? So the parallel plate modes cannot propagate through this system of patterned copper, right? And we're not using vias or any other complicated mechanism. This is just modal coupling. And this arises, of course, from our in-depth knowledge of multiconductor transmission line theory and our engineering of these modes to create the suppression. So then we went and we extended this idea to suppressing parallel plate modes in microstrip patch antennas. So our idea was that we could affect two different cavity modes, cavity resonant modes, at two independent frequencies, right? So inside of a microstrip patch antenna, of course, it operates by having a TM10 type cavity mode. And we placed an EBG, a metamaterial electromagnetic bandgap structure, on either end of this resonant cavity. And we designed the metamaterial such that at one frequency, the fields would propagate through the metamaterial at 2.4 gigahertz, indicated on this dispersion diagram, shown on the left. And we see that in the fields, shown in the bottom left. Then at a higher frequency, inside of the bandgap region, we see that at 5 gigahertz, the fields are contained inside the EBG. So we have the same resonant cavity mode, but it exists over an electrically shorter length, such that it resonates at a higher band. And so this is sort of ideal for antennas, I think, because we have the same cavity resonance at the two bands. We essentially have the same radiative properties of the antenna at the two bands. And so this is very advantageous when designing these dual band antennas. And we did the same thing for circular patch antennas in a GPS antenna. So again, looking at the right-hand side plots, we see that at the lower band, GPS L2 at 1.228 gigahertz, the fields propagate through our metamaterial region around the outside of this patch. But at GPS L1 at 1.575 gigahertz, the fields are contained inside of this ring. And so we have the two different resonant modes. Now, this concept of integrating metamaterials into PCB environments was also extended to microstrip structures. So what was originally found quite some time ago, primarily analyzed in the work of Dr. Islam, was that these transmission line metamaterials could be embedded into coupled microstrip systems to enable a variety of devices, in particular couplers. And what he found was that by loading one of these microstrip sections with a series capacitors and shunt inductors, that again, a band gap could be formed because the other microstrip would support right-hand propagation, whereas the loaded one would support left-hand propagation. But specifically in this coupling region, there are actually evanescent modes that exchange power between the two lines. And what he found was that he could analyze the degree of power being exchanged and use this to couple power and form this metamaterial coupler. So he was actually able to design this microstrip-based coupler in a very compressed space. It's a very miniaturized coupler because we're using strong lumped reactive loading, right? So the phase constant is much smaller traveling through these transmission lines than it would be in an unloaded transmission line. And as such, it affects miniaturization to a very high degree. Another application of embedding metamaterials into microstrips was this idea that we could use different bands supported by the metamaterial around the band gap, as shown in the left-hand figure, to achieve the same phase shift at two different frequencies, right? So we know, of course, a microstrip, an unloaded transmission line, will support a phase that's proportional to the frequency. But now that we've introduced this sort of very complex dispersion phenomena, we can actually engineer it such that there's not a strong correlation between phase and frequency. So we can design the phases of this metamaterial transmission line to support the same phase at pretty much any desirable frequency that we want. So we use this to, again, design a coupler. But in this case, we actually designed a hybrid coupler, which showed similar performance at two frequency bands. This is, again, a GPS coupler. So it operates on the right. You can see by the scattering on the right-hand plot at the frequencies indicated by the vertical lines, GPS L1 and L2 at 1.228 and 1.575 gigahertz. And an important point to note here is that all we've done is we've taken this metamaterial transmission line and we've embedded it directly into the existing microstrip. So there's no increased space to the structure. It's literally just removing some copper out of the existing microstrip. And we find this very interesting because we've effectively augmented an existing structure with just a very simple modification, along with some very in-depth understanding of how this metamaterial works. As well, we've shown that we could implement these metamaterials in a sort of different arrangement in order to affect frequency-dependent routing of signals. So what one of my colleagues, Braden Smith, did was to develop a dual band Wilkinson power divider by propagating signals through one branch of transmission line at one frequency, as indicated by the dashed line on the left, while forcing these signals to route through a different length of transmission line, as shown by the larger dashed curves on the outside of that structure. And as shown on the right-hand side, we see similar scattering behavior at those two target frequency bands. And I should point out that these bands aren't just coincidental. We can tune these metamaterials to support these bands wherever we want. And that's just one advantage of the dispersion engineering capabilities of these metamaterials. Another one of my colleagues, Jacob Brown, investigated using these metamaterials in a different topology using a very, very small band gap, so a very small coupling of power between these modes to affect a narrowband filter in a microstrip topology. So as shown on the left-hand side, a very small band gap width is supported by this structure. And the realized structure shown in the middle, you can see we've just implemented a capacitor into the strip line of this coplanar waveguide structure. And this gives us the very small but controllable band gap shown in the scattering on the right-hand side. So there are numerous other applications that I haven't gone into, but I think those ones really demonstrate the power and the capability of multi-conductor transmission line metamaterials to affect novel wave manipulation behavior using this understanding of how we can insert terminal domain components to affect modal domain responses. So some future work of this application is, of course, extension to multi-dimensional multi-conductor transmission lines. So we can see on the figure on the left, we can analyze, or we could analyze more elaborate networks to really predict the behavior of multi-dimensional multi-conductor transmission line metamaterial networks. And we could use this in multiple different applications. For example, lensing applications, shown by this Rotman lens in the middle figure there. We could implement a metamaterial here to create this sort of type of behavior, perhaps in a very miniaturized form factor, or with a very predictable output in a more sort of analytically rigorous form, perhaps. Of course, volumetric 3D metamaterials have been investigated, but this type of structure really lacks a multi-conductor formalism for how to analyze the structure. And we could do things like beamforming, as is done with modern metasurfaces, as shown on the right. So one of the interesting facets of multi-conductor transmission line metamaterial Bloch modes is that they contain their own modal properties, right? But one thing I haven't mentioned is that there is actually an unsolved problem in multi-conductor transmission line theory, which is how we determine the properties other than dispersion or propagation of these multi-conductor transmission line modes. And specifically, this comes about as a result of the fact that we know from linear algebra that the eigenvectors, these matrices TV and TI, the columns of these matrices may be arbitrarily scaled, right? That's comes straight out of linear algebra. So if we're using these matrices in the terminal to modal domain transform, right, what we find is that various modal quantities, such as per unit length, admittance, and impedance, or characteristic impedance of these modes, are also arbitrarily scaled, depending on our choice of scaling factor from the eigenmode process. So it's understood that these modal values may not be uniquely defined. But does this actually make sense? If we're looking at a wave propagating through this metamaterial, does it actually have an undefined impedance? This is actually the topic of my PhD research. I'm confident that we've been working towards a solution towards both these problems and the applications on the multi-dimensional side. The work is not quite published yet, but I look forward to discussing it shortly in the near future. So thank you for your attention to my presentation. Are there any questions?
Okay, thank you, Stuart. It was a good, nice talk to listen to. I hope we have any questions. So if there are any, can people please raise their hands? Okay, don't see. I think we have a question from Polina.
Yes, hi, Stuart. Thank you very much for really a very, very interesting talk. So, look, I was thinking about, is it possible to include some kind of nonlinearity to your multi-conductor transmission line, like introducing some varactor diodes, and what kind of effects you would expect to have in this case?
Oh, thank you for the great question. Yes, we can in fact do that. While we typically do things like use these linear components, right, just capacitors or inductors, etc., the ABCD formalism that we use to analyze these structures actually allows us to put any arbitrary component in, as long as it's describable by in terms of its voltages and currents, right, by this ABCD formalism. So yeah, we can indeed put a nonlinear component in. We would have to include the effects of doing a sweep on, let's say, the level of voltages and currents, etc. But the ABCD formalism and the extraction of the Bloch modes actually does allow for the modeling of non-reciprocal phenomena. So this would enable us to have things such as a dispersion diagram, which has a different behavior on the positive side of phase than on the negative side of phase, right? So in all these diagrams, I've just assumed, let's say, one side. But we could get some very interesting effects if we were to include non-reciprocal or non-linear components like that, yes.
Thank you. That sounds pretty great and interesting, probably to continue in this direction. Okay, so any other questions, guys?
I had a question about the general part of the introduction about the modes, because I think we have some stuff like that in when we designed the resonators for MRI. I was wondering if you can theoretically predict how each of the distribution of the model distribution, the model representation would say look in terms of the terminal representation. So, like, can you somehow visualize the modes that exist in the structure, and does that somehow provide you a way to more efficiently excite each of the modes in there?
The short answer to your question is yes, we can. So again, that information relating the two domains is contained in these eigenvector matrices, TV and TI. Right. So what we can do is we can actually, in our metamaterial case, plot the entries of these matrices as a function of frequency, let's say, and that will give us the distribution of currents or voltages corresponding to each mode. So that's actually been done in some other works. I didn't elaborate on that here, but I think it's a pretty well-known process in multi-conductor transmission line theory.
Okay, so thank you. And did I have some? Do you have anything else in the chat? No, we don't. Yeah, I also had a question when you spoke about the band gap as a coupling of the forward and backwards propagating mode. So when you mentioned that, does it mean that there is actually some current flowing inside? So as a sort of difference between the two modes, so does it mean that even if there is a band gap and things like the wave is reflected, there is some current excited in the conductors of the transmission line?
Yeah, for sure. There are currents and voltages excited for the various conductors, which support the power that we see. But of course, the voltages and currents that propagate inside of this structure, if we look at a finite cascade, we see that those quantities were evanescent, right? They would be diminishing as the wave propagated through the material.
Okay. Yeah. Yeah, okay. I don't think we have more questions. So thank you, Stuart.